Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. All right, let's begin our module number 3. So this is a module that I'm going to review some machine learning concepts and models. I'm going to do it in 3 parts. In part 1, we will be quickly reviewing machine learning fundamentals. I assume that you have some backgrounds in machine learning, and this part should be a quick refresher for you. In the second part, I'm going to review some of the most powerful models when it comes to machine learning, namely the boosting models. Well, I will specifically cover XGBoost, CatBoost, and LightGBM. And then finally, in the third part, I will talk about some challenges that you might face when you're dealing with the time series data. Because handling time series data when it comes to machine learning, it's a little bit tricky, and we should make sure that we are considering all the aspects of time series. Okay, so without further ado, let's jump into it. Okay, so part 1, machine learning fundamentals. So in this part, I'm going to review these concepts. So firstly, machine learning versus traditional programming. We're going to see what is the main difference between the two. Then we're going to go over different types of machine learning, namely supervised, unsupervised, and etc. Then we're going to see what is this thing that we're going to call it a model when it comes to machine learning. We will quickly review some evaluation metrics, and we will get to this very important concept in machine learning, which is bias variance trade-off. Basically, we want to discuss this idea of optimization versus generalization. Then we're going to see how we're going to split the data into train, test, and validation sets, and we will explore what if the data set is not large enough. We have to do some resampling techniques. And in the last 3 parts, we're going to explore how the machines actually learn. In order to explain that, we have to define the cost function, and then we have to see what are those solvers or learners that are going to optimize over the cost function to give us the weights of the model. All right. Okay, so what is machine learning? Machine learning, as we talked about it in the previous modules, is a subset of AI that enables computer to learn from the data. Okay, so this is different from the traditional or classical programming in a sense that, look at this one. This is classical programming. In classical programming, the inputs are some data and some rules. So for example, you have been given x and some rules. So let me show it with f of x, right? So this f of x can be anything. Let's keep it very simple. It's equal to x plus 3. So I know the x, I know the rule, and then the computer is going to do the math and it's going to calculate the output, right? So for example, and this output I can label it as y. For example, if x is equal to 3, or let me use a different number, if x is equal to number 6, then the output is going to be 6 plus 3, which is equal to 9, right? So this is classical programming. There's no uncertainty. The inputs are given, the rules are given, the computer is going to do the math and give you the output, right? However, in machine learning, the story is different. You have been given some inputs. The input can be x's and answers, right? So depending on the type of machine learning, sometimes you will be given the answer, sometimes you won't. This is the difference between supervised versus unsupervised. But let's keep things simple. So imagine you have the x's, you have the y's, and the goal of machine learning is to learn from the data, right? So this is the goal, to learn from the data. What are the rules? What were the relationship? What was the underlying pattern between x and y? So that's the goal. The goal in machine learning is to estimate this f of x. Let's show it with f hat of x, right? So this is the pattern. This is what we are looking for in machine learning. Okay, so as we said, so this means that the machine learning system is trained with bunch of rules and algorithms. So it is trained rather than being explicitly programmed. So whenever we say that machine learning is a system that's not explicitly programmed by human, this is what we mean. However, this does not mean that it's not human involved. We, the humans, are the ones who are going to set the scene, who are going to set the rules or algorithms. Okay. Now, we know that machine learning involves in automated detection of these patterns in the data and apply those patterns to make some predictions, right, on the unseen data. So the optimal goal in machine learning is to maximize the performance of the model on the unseen data. So it's all about generalization. How good your model is in terms of generalizing of predictions on something that the model has never seen before. That's the optimal goal in machine learning. All right, now that we know what is machine learning, let's look at different types of machine learning. The most common one is called supervised. In supervised machine learning, the data is labeled. So what does it mean is that we have both x's and the labels of the x's. So whatever your target variable is, it is known. So for example, if you're doing regression analysis, if you're doing a housing price, you have the features and you know the price of the house as well. If you're doing classifications, you have the features and you know if a client defaulted or no default. So you know all these things, and the machine is going to learn the pattern and come up with some predictions. And at the end of the day, you can compare these predictions with the actuals to just make the model better. You know, if these errors are small, it's a good. If the errors are large, so we have to go ahead and make the model better. So that's the supervised. In unsupervised, the story is a little different. We only have x's. There's no label here. There's no target variable. And that means that the output is going to be a little fuzzy. So what are we looking for? So in unsupervised, usually we're looking for basically what is the underlying pattern in the data, in the inputs, right? We're looking for some representation of the data. So the examples are, we use unsupervised learning for clustering, anomaly detection, and dimensionality reduction. So imagine you have a data set with thousands of features, and you want to reduce the dimension of the data just because of for visualization, right? So you cannot visualize something in 1,000 dimension, but you can reduce the dimension, let's say, into two components. We can use principal component analysis, PC1 and PC2, and then do a simple visualization and see where the clouds of data are standing. Okay, so this is called unsupervised. The third one is semi-supervised. So semi-supervised is a combination of supervised and unsupervised. And the way that it works is like this. So you have, imagine these are your features and this is your target variable. And for part of the data, let's say for this part, we do have both the features and the labels. But for the, let's say, most of the time for the majority of the data, you only have the x's, you have the features, you do not have the labels. So the goal is to use machine learning models to figure out, based on this part of the data, to figure out what is the relationship, what is the pattern, and then apply that pattern to this part of the data to come up with some labels. We call it meta labels for this part of the data, which is unlabeled. And we're gonna then we can go ahead and use this meta labels to train the entire model. So that's for the semi-supervised. The next one is self-supervised. So self-supervised learning is a type of unsupervised learning. So, but it has the property that the learning process itself is being fed with the data itself. So what it means that, so let me give you an example. You've been given a sequence of text and your job is to predict the next word, right? Or imagine you have an image and part of the image is blurry and you want to train the model based on whatever it is in the data set and to come up to replicate this blurry part, right? So this self-supervised is usually used in deep learning applications rather than machine learning. And the last one is reinforcement learning. So in reinforcement learning, there is this agent living in an environment. So we have an agent which interacts with the environment. The agents can take some specific actions. So we are going to define the actions. So for example, it can go up, down, left, right, or in stock market, it can buy, sell, or hold, right? So this agents there are going to be some specific actions that it can take, and it's going to take those actions to maximize a reward from the environment, right? So based on the reward, the agent is going to get feedback from the environment and then just repeat this process thousands or millions of times by doing random exploration and exploitation. Okay, so at the end of the day, the goal is by maximizing this reward function, the agent is going to learn something called policy function. At whatever state in the environment the agent is, what is the optimal policy? What is the best next move? So this is the output of the reinforcement learning, something called policy. All right, so this is at the very high level, different types of machine learning. And again, I assume that you have some backgrounds in machine learning, and this should be a quick review. All right, now we're going to go through some set of slides that help us explain how the machines actually learn. So we have to see what is that model, what are the performance metrics, what is bias variance trade-off, and what is the cost function, and how do we optimize that cost function. So let's start by the model. So this is a simple machine learning model. The machine learning model is a function of some input variable and some parameters or hyperparameters. And of course, as we said, this is different from traditional programming. It means that it involves some uncertainty. There is no true model out there, right? So that's why we have to add this noise. The dimension of the data is going to be m, so we have m dimensional feature space and let's say k parameters and hyperparameters. So our y variables is sometimes called response variable, dependent variable. In machine learning language, we usually call it target. Our x variables, these are predictors, independent variables, and again, in machine learning language, we call them features. And thetas are our estimates or specifications or parameters of the model. Okay, so it's all about estimating this f by something called f hat. So this is the goal in machine learning for two purposes. One, for inference. This is the interpretation part of the machine learning. The other one for prediction. You know, how model is doing a good job in a never seen before data set, right? Okay, so now let's say we have a model. How do we quantify the performance of the model? So generally, if it is a regression, we're going to use some basic performance metrics like MAE, mean absolute error, MSE, mean squared error, root mean squared error, and this is root mean squared log error. Then we have r square and adjusted r square, and we can have again lots of different metrics as well. We can have MAPE, which is mean absolute percentage error. We can have SMAPE, you know, symmetric mean absolute percentage error, and you name it. You know, depending on the model that we have, depending on the nature of the target variable, we may end up using different performance metric for regression. For classification, same story. You know, the most important one is what we call confusion matrix, and based on that confusion matrix, we can go ahead and define bunch of or dozens of statistics, performance metrics like accuracy, precision, recall, F1 score, you know, AUC, ROC as well, and again, entropy, cross entropy, Gini, and you name it. In the machine learning course, we have talked about almost all of these performance metrics, but the goal is that we come up with something that can quantify this measure of our error. What is the distance between the predictions and the reality? Okay. All right. Now let's talk about a very important concept in machine learning, which is called bias variance trade-off. So what we have here in the graph, on the horizontal axis, we have model complexity. As we go from left to right, the model is going to become more complex. For example, in linear regression, we start with a very simple linear function, and then we make it more quadratic to the power of 3, to the power of 4. We're going to add interactions and etc. We're going to make the model more complex as we go from left to right. On the horizontal axis, we have a measure of the test error. For example, if it is regression analysis, we can look at the mean squared error in the test set. Okay. Now, I want you to look at the graphs at the top, right? So if the model is too simple, we say that, let's say this is your train set and we are using the model, and let's say this is our estimation. The model is super simple, actually. It's going to give you the average, right? So the idea is that this model is what we call, it has high bias. It means that if you repeat this process, if I worked with different subsamples and I use the same model, this on average is far from reality. It seems that in reality there is this curvature relationship in the data, but the model is not capturing it. No matter how many times you repeat it, on average it's not hitting at the target. We say this model has a high bias. So high bias, I can show it here. So the model has very high bias. This is a very simple model, but the variance is small. Model variance is small. What does it mean? It means that, again, if I use another subset of the data, maybe it's going to be a slightly lower, slightly higher, but on average, we're not hitting at the target. So the variance is small, the bias is high. A combination of the two, which is, for example, a mean squared error in the test set, is going to be super high, right? So that's what we call the model is underfitting. On the other hand, if the model is too complex, we call it's overfitting. What does that mean? So look at that. The blue dots are the true observations. And if you make the model super complex to do something as crazy as this, of course it's doing a perfect job in the train set. But the problem is that this model does not generalize well. If you apply it to a test set, to a new data set, it's going to have very, very high variance, right? So, but the idea is that look at the bias though. Again, imagine I work with the other subsamples. Let me use another color. and I use this super complex model. The idea is that on average, though, it's hitting at the target. So on average, it's capturing this nonlinearity. So it has low bias, but the problem is that the variance is super high. So it has, we are here now, it has low bias, but the variance is super high. And again, a combination of the two is going to be very high. So either we are underfitting or overfitting, we're in the wrong part of the curve. So what is the optimal? A good balance between bias and variance is somewhere in between, that on average you capture the true relationship in the data, and at the same time, if you work with different samples in the data, the variance is not that high, so the model variance is not that high. So you get a good mix of the two, and it's going to minimize your, for example here, your mean squared error in the test. Okay, so this is a balance between bias and variance in a nutshell. Another concept that I want you to be aware is, it's very similar to bias variance trade-off, is something we call optimization versus generalization, right? So your model should be able to optimize well in the train set and at the same time to generalize well in the test set, right? So what I mean by that, so imagine we have something like this. I'm looking at cross-validation, let's say errors, and I'm looking at the performance in the train set and the test set, right? And I'm making the model more complex as I go from left to right, right? So in the train set, a good model is something like this that, so I'm gonna look at, so the blue one is, so this is error, the blue one is train set error, and I'm gonna use another color, the red one, for cross-validation error, right? So a good model is a model that can learn something if you make it more complex. So this is very, very important because your model should be able to learn something. If you have a model like this, so for example, I'm going to go ahead and erase it later on, but if you have a model like this, no matter how complex you make the model, it's not reducing the error. It's not a good model. You have to do something about it, right? So a good model is a model that is able to optimize over the train set. So that's one thing. And the other thing is that the model should be able to generalize well as well. So it means that if I plot the cross-validation errors, the red one, it should be able to decrease. And of course, at some point, it will increase. So this is the part that the model is going to overfit. If I make the model too complex, it's going to perform very bad on the cross-validation set or in the test set. So this is a sign that your model is overfitting. And if the model is overfitting, you have to regularize it and go back a little bit, find the optimal value that's going to optimize the cross-validation error. This is really, really, really important. A good model is a model that can overfit. If your model cannot overfit, so if you plot the performance in a test set or a cross-validation set and you don't see this behavior, then it means that you don't have a good enough or flexible enough model in your hands. So you have to somehow do something about it. You have to change the structure of the model that you're using, right? Once you have a model that can overfit, this is good news. You can go ahead and prune it back or regularize it to make it less complex and to get to a point that it's able to generalize well as well in the cross-validation data or in the test data. I hope this idea is clear, and but be aware that a good model is a model that can overfit first place, and then in the second place, it's time to optimize it. It's time to make sure that it can generalize as well in the test set. Okay, so to recap the concepts of overfitting, overfitting happens when the fitted algorithm does not generalize well to new data. So this is an example for regression. Here's what we have overfitting, right? Again, it's doing a perfect job in the train set, but it does not generalize well in the test data, because if this is a test data, you can see the black dotted line or dashed line is not doing a good job at all. And this is an example for classification. Again, we are pushing it too much. The model is too complex, and we are unnecessarily capturing these things correctly in the train set, which we don't need it, right? This model does not generalize well. The model fits the train data too well while not predicting well in new data. So these are different versions of defining overfitting. The model fits the noise in training data, find a pattern that does not exist. So basically you're memorizing the pattern, right? So you can make the model super complex and memorize the data, memorize the pattern to get it, let's say, train error of 0. And the algorithm has simply, as I said, is basically is memorizing the data rather than learning anything from the data. So it's not going to be generalizable. And this happens when your model is too complex. But again, don't get me wrong, it's not necessarily a bad thing. You want to make sure that your model is able to overfit. This is an important one. Once you get a model that is able to overfit, then you're going to regularize it back to make sure that it's less complex than what it should be. All right, so we said that having a model that overfit is not necessarily bad. Actually, we want to have that model, right? But let's say we have that model, how can we fix this overfitting part? There are different ways to do that. The first and most common one is collecting more data, okay? So for example, look at this. Let me use the right marker. Look at this data set here, right? We have 1, 2, 3, 4, 5 observations. If we have only these 5 observations, we can make the model complex and get this kind of pattern, right? However, if we collect more observations, which is going to fill the gap here, then we get to the next chart. This is a data set with more observations, and as you can see, the model is able to fit the data a lot better with a simpler model, right? So this is collecting more data. What I want you to be very careful is that collecting more data does not always work, and there's a reason for that, because what if your data that you're adding is simply just noisy and there's not much to learn from that data? So let me give you an example. Imagine you have, this is your error, and this is your model complexity, okay? And you are doing, it seems you get something like this. No matter what you do, this is the performance of the model in the train set. Even in the train set, you cannot reduce the error as much as you want. So for example, this is your benchmark, or maybe lower than this. This is a benchmark, so this is benchmark error, and by no means you're getting close to that benchmark error, no matter how much you make this model complex. Guys, pay attention. This is a train set performance, right? Usually the train set performance should be something like this, right? But if you get something like this, it means that your data is not just getting it. The data is not informative in terms of explaining the target variable. So if that's the case, don't waste your time. Collecting more data is not going to help. So the next approach that we can combat this overfitting is what we just talked about, is right, some regularizations, complexity reduction. So for example, we go from this super polynomial model and we add some regularization terms. We're going to penalize this regression for having higher polynomial degrees, and it's going to make it to less complex by something like this, right? So these are different techniques. Again, one other techniques for complexity reduction is feature selection, basically engineering the features and come up with more informative features, hopefully to explain the target variable with simpler data. And then finally, we can always use our cross-validation and look at the performance in the cross-validation to come up with a better trade-off between bias and variance. So this is what we covered in the previous slide, right? So we use cross-validation, or in deep learning we do the validation set only sometimes, to figure out what is a better combination between the optimization versus generalization, between bias and variance, okay? All right, now let's quickly review the idea of partitioning the dataset in machine learning. I know you're quite familiar with this, so I'm going to speed up a little bit here. So what do we mean by partitioning? So we're going to partition the data. Ideally, we're going to partition it into 3 parts. So the train part, the train set, validation set, and test set. Right? There is no right or wrong rule, but depending on the size of the data set, usually we do 70%, 70 to 80% train and validation, and 10 to 20% or 30% test set. But again, depending on the size of the data, we can treat it differently. If you have millions of records of data, you don't need to keep 20% of it for test set. You can only keep 5% or 2%. But if you have thousands of data, you need 10 to 20% for the test set. Okay. So we use a train set to train the model, we use the validation set to validate it and tune the hyperparameters of the model, and we use a test set, so this is the most important one, to test the model's ability to see if it is generalized well or not, if it makes predictions, good predictions on the not ever seen data. Okay, so to be valid and useful, any supervised machine learning models must generalize well. So this is important, right? And beyond the train set. And now the point is, what if we don't have the large data set? What if we don't have millions of records of data that we can simply have enough information in the train set, enough information in the validation set, and enough data in the test set? What if that's not the case? And in so many machine learning examples and in the industry problem, that's the case. We don't have unlimited data. So how we do? All right, so what is this resampling method? So we know that you're talking about if this data set is small, and we want to divide it into train and validation, right? If the train set is small, the model is not going to learn anything. If the validation set is small, the model is not going to be able to do a good hyperparameter optimization. It's not able to tune the hyperparameters properly. And we will see that in practice, the model performance in the validation set is going to be very unstable. It means that if you do it for different validation sets, you're going to get very different performance metrics. The variance of the performance metric is going to be large. So what is the solution? The solution is combining these two sets together and use a technique called cross-validation. Okay, so the most common techniques in cross-validation is called k-fold cross-validation, and the idea is pretty straightforward. And the thing is that you're going to divide the train data into k roughly equal size and non-overlapping groups, right? And so let's say k is equal to 5 in this example. So I'm going to divide the data set, the ones excluding the test set, right, into 5 parts: 1, 2, 3, 4, 5, right? And then I'm going to hold k minus 1 part, 4 parts as a train set, and 1 part as a validation set, right? And I'm going to repeat this process for every single time that we have a separate validation set. So if k is equal to 5, so I'm going to have 1, 2, 3, 4, 5 different iterations, right? So for example, here the model is going to be trained on these 4 folds and make predictions on this fold. Here the model is going to be trained on these 4 folds and trained on this fold, right? And in terms of the performance, we're going to aggregate over all the performances, right? So for example, if it is regression, we're looking at the R-squared or mean squared error. We can simply go ahead and aggregate. As you can see, this method is going to be a lot more stable compared to doing this only once. But at the same time, if it happens that you have a very small data set, right? So you have a very small data set and you want a high accuracy. The problem is that you do cross-validation and you realize that the variance of these performance metrics, let's say MSE in the cross-validation, is high. If the variance is high, it means that whatever you're doing in the validation set, the performance is very different each time. So there's a solution to that, which is called iterative k-fold cross-validation, and it's specifically designed to come up with a more stable path for cross-validation, right? And again, that idea is very simple as well. The thing is that you can repeat this entire process p times and call it iterative k-fold cross-validation. As you can see, you can get more stable path for cross-validation performance, but the problem is that it is very high, it is very costly because cross-validation itself is computationally expensive. If you want to do p iteration of that, it's going to be even more computationally expensive. But I just wanted to be aware that there are methods to work with very small data sets to get a stable cross-validation performance. All right, to wrap up this part, let's talk about why do we use cross-validation. So we use cross-validation in practice for two main reasons. The first one is model architecture selection. So this is the idea of optimization versus generalization that we already discussed, right? So the idea is that, okay, which one is the case? If you're talking about simple polynomial regression model, is this a right model, or is this a right model, or is this a right model, right? So and the way that we figured it out is we plotted cross-validated error versus model complexity, let's say polynomial degree, and we realize that it behaves something like this. This is going to be my optimal polynomial degree, and maybe this is the answer. Okay, so that's the first reason we use cross-validation. Model architecture selection. within the same family of models, what is the best set of hyperparameters? If it is linear regression, what is the best set of hyperparameters? If it is random forest, what is the best set of hyperparameters? The second reason for using cross-validation is to get a fair estimate of the model performance in a test set, right? Because after all, when we are doing cross-validation, let's say 5 folds, 1, 2, 3, 4, we are training on these 4 and making a prediction on the fifth fold, which is a validation set. So if we do not overkill this process of cross-validation, it is a fair estimate of the performance of the model in a test set, in a set that the model has not seen those observations. But this comes with a caveat. If you overkill this process, if you do the cross-validation a lot, so there's going to be a data leakage from validation set to the model. And this is a big if, because it's gonna overfit. If your model is overfit in the validation set, then you're gonna get fake good performance, right? So you have to be careful. So once we train the model in the train set, once we come up with a best architecture of the model using cross-validation, it's time to make prediction in a test set, right? So we estimate the generalization error or test set error using the test set. And then we're going to compare different families of models using the performance in a test set, right? So for example, at the end of the day, I have 4 or 5 different families of model: linear regression, logistic regression, random forest, XGBoost, you name it. The way that I compare these models with each other is based on their performance on the test set, not the cross-validation set. I hope that this is clear. What is the difference between why do we use cross-validation, and when we use the performance of the model in the test set. All right, before we move on to the solvers and optimizers part, so let's talk about yet another curve that's going to help us to answer this question. Do we need to collect more data, right? So this is called learning curve, and it's very important, and it's a very intuitive one. A learning curve is a plot that shows the relationship between the training set size from one hand and the performance of the model from the other hand, okay? It is basically used to diagnose that if your model is going to have a high bias, high variance, or it's just fine, it has the right combination of the two, right? So let me give you an example. Imagine, so this is a very important one, pay attention, because this is usually confusing for students to understand. So imagine this is your model, okay? So your model is a very simple quadratic function. Let's say y is equal to, it's very simple, just x1, and this is your y. Y is equal to, let's say, some bias term plus w1 x1 plus w2 x1 squared. Very simple model with some noise, right? If this is the model. Now I'm going to say, okay, this is the model. Now if the train size is just, let's say this is the only train size, right? And that's your model. Your model is perfectly capturing that one if you only have 2 observations. So if you're here, let's say 2 observations, if I have 2 observations, the error is 0, right? Because the model is going through those points in the train set and it's doing a perfect job, right? However, not surprisingly, the performance, so this was the performance in the train set. The performance in the cross-validation set or in the test set, it's going to be way worse, right? Because maybe in the cross-validation, we had observations like this. And we know that this model is not capturing anything, right? So the performance in the cross-validation set when the observation number is small, it's going to be very, very bad. Okay. Now let's start increasing the number of observations, right? So let's say we add a bunch of more observations. We get something like this. Okay. And now as we increase the train size, of course, the performance of the model is going to get worse because now we have more information and the model needs to fit the more information. And I want you to focus on the blue ones here only. Let me erase this one. Just the model needs to focus on more information, and maybe it's not necessarily doing a good job for these observations, right? So what it means that the error is going to increase. Your measure of performance in terms of error is going to increase as the train set size increase because it's going to have harder time to fit the model. But on the other hand, this error is going to decrease for the test set or for the cross-validation, right? Because again, if this is a cross-validation data, it's going to be a lot better than this because we have more information now. So we get to a point that these 2 curves are going to converge, right? Now, now you have to look at the your benchmark performance, right? Or we also call it common sense performance. Imagine this is your benchmark performance. If your model is not able to predict well for large size in the train set, even for the train set, right? So if your model is not outbidding the benchmark performance even in the train set, it means that your model is suffering from a large bias. So the bias is high. No matter how many iterations you do, no matter how large the sample size is, on average, your model is not hitting at the target. You know what? Maybe the target was something like this. Maybe the model needs to be polynomial to the degree of 3, right? So that's where you figure out that, okay, this distance is high. It's not outbidding or it's not beating your benchmark performance, but they're converging to each other. So it means that you have a high bias problem. Okay, so that's a high bias problem. What is the high variance problem? High variance problem happens when the gap between this performance metrics between validation sets and train set is large, and it remains large no matter how much you increase the train set size, right? So let me give you another example to make sure that you understand why this gap may remain large. Okay? Our true model is good, and actually it's, let's say, using the same observations from the previous example. Imagine we got the right model. It should be something like this, right? Y and X. But the problem is that this is your train observation. This is your maybe cross-validation observations. So maybe we get some observations here, right? So it seems that in cross-validated, the model is not capturing the performance well, simply because we don't have enough observations, right? If we keep adding more observations, right, if we go to the right, these two curves should converge eventually. We should get to a point, something like this. So if the gap is large, this is a sign that your model has high variance, and we can fix it by collecting more information. Okay, so and when it is when you plot the learning curve, a just right model is, let me actually show it to you. So what is a just right model? So you have the cross-validation score that decrease relatively fast, and then the train score that increase relatively again fast, and for a decent amount of data we are outbidding the benchmark as well. Hopefully we're outbidding the benchmark as well. So this is a just right fit between bias and variance. Okay, so that was the learning curve. All right, so we are finally ready to answer this interesting question of how do machines actually learn. So at a very high level, we know that, imagine this is our machine learning box. We have some inputs, we have the labels, the model learns the patterns and makes some predictions. And at the end of the day, we're going to compare these predictions with each other and then try to optimize the weights and coefficients of the model, that this performance metrics is going to become better and better and better. So in a nutshell, to answer this question, how do machines actually learn, is by optimizing or minimizing the cost function. And what is the cost? The difference, the distance between actuals versus predictions. Okay, now let's look at the formal definitions. Okay, so starting by learning. What do we mean by learning? Learning is this process of finding the model's weights and or the value of the parameters and hyperparameter. What is the cost function? Cost function tells us how good or bad the model is at making predictions given a set of parameters and hyperparameters, right? And so each cost function has its own curvature and its own gradients. And the slope of the gradient, well, basically, gradient is the slope, right? The sign of this gradient is going to tell us how we should update the parameters to make the model more accurate. So very naively speaking, imagine this is the parameter of interest that I'm optimizing over. Let's show it with theta. And this is my cost function. Let's show it with j of, it's a function of inputs and theta. And imagine it's very simple, something like this, right? And at each point, I can go ahead and calculate the slope. So here, for example, the slope is positive. If the slope is positive and we're doing a minimization, where should I go, left or right? Yeah, I should go left, right? So I go to the next point, next point, next point, and hopefully I get to the minimum. If I start from here, look at the slope. Slope is negative. So where should I go? To the left or right? The answer is right. So as you can see in this very simple example, we are going in the opposite direction of the sign of the slope, right? And so we're going to formalize it more mathematically. But so in general, there are two most frequently used optimization algorithms, and they are namely called gradient descent and stochastic gradient descent. So let's see what is gradient descent and later on why we have to extend it and go beyond gradient descent and use something called stochastic gradient descent. All right, so let's start by the gradient descent definition. It's an iterative optimization algorithm, right, for finding the minimum of a function. So we know that no matter how we define the cost function, we want to minimize it, right? And hopefully, as the name suggests, we want to decrease the gradients along the way. Hopefully, we get to a point that the gradient is equal to 0, right? So we start at some random points and take steps proportional to the negative of the gradient, to the opposite direction of the gradient. And here is the mathematical formulation. So we have theta. Theta is our parameter of interest. And then we have alpha. This is what we call the learning rate. What are the magnitude of the steps that we go to the right directions? And then finally, this is our cost function, and this is the gradient of the cost function, right? So again, if I want to show you visually, I have this function, the cost function of x and theta, and then this is my parameter of interest. Imagine this is our very simple cost function. We are assuming that it is continuous and it's very well behaved, right? And then we start from random points. If I start from this random point, then I calculate the gradient. It's a number. Let's say it's +1. It's a number. I plug this number here in the gradient, and then I multiply it to something called learning rate. Let's say learning rate is 0.5. So alpha multiplied that gradient, this is 0.5. So I get minus 0.5 here, minus 0.5. And imagine your initial value for theta, again, naively speaking, let's say we start from number 4. So we do 4 minus 0.5, we get 3.5. So we get to this point, 3.5. And we keep repeating this process, right? We keep repeating this process, we get to a point that, let's say at this point, this is equal to 2, and the gradient is equal to 0, right? So we say, okay, if I want to optimize the theta, theta is going to be equal to 2 minus my alpha, 0.5, multiply the gradient, which is 0, it's going to be 2. So I will get stuck here. So this is the optimal value. The same story happens if I start from this random point. Again, the slope is going to be now, let's say, -1. I need to, and let's say, again, just for the sake of argument, imagine this is point, I don't know, 1 or 0.5, whatever. And then I say, okay, the new theta is going to be 1 minus the learning rate, 0.5, multiply the gradient, which is -1. So I'm going to get 1.5. So as you can see, we're going in the opposite direction, 1.5. Again, these are just, I use very simple numbers. In reality, it might be a little different. The steps are not necessarily symmetric, and etc., depending on the size of the shape of the cost function. Okay, hopefully it gives you a sense that how gradient descent at the very high level is working. All right, now let's talk about the choice of learning rate alpha. Well, if this alpha that we're talking about, the learning rate, is too small, what's the problem? The problem is that the gradient descent can be very slow. I want you to focus on this chart. And again, theta versus your loss function. A small learning rate requires many, many updates before reaching the minimum points, right? So for example, we go from here to here, and as you can see, it requires a lot of iteration. And the problem is that each iteration is using the entire train set to update the parameters. And if the train set is millions of records of data, so and if the model requires so many of these iterations to get to the minimum point, as you can see, it's going to be computationally expensive, right? On the other hand, if the alpha is too large, then the gradient descent can even diverge. We say it can jump over the minimum, or it can even diverge. So let's say, let me show you an example that it can jump. So for example, we start from here, and then imagine alpha is very large, and instead of going this way, we go this way. So we pass the minimum, right? We pass the minimum, and this is a problem. And sometimes the alpha is so large that instead of going even in the right direction, we go completely in the wrong direction. We diverge. So that's a problem of a too high alpha or learning rate. So hopefully we have to figure out what is the just right or optimal level of alpha. With the smallest number of iterations, we get to the point that the gradient is equal to 0. Okay, now the question is, why should we go beyond gradient descent, right? There are some important disadvantages of gradient descent that makes us wonder, can we do it even better? And the answer is yes. So what are the disadvantages? First of all, and I think this is one of the most important one, is that the gradient descent is single batch. So what it means that it's going to use the entire train set to update the parameter. So as I said in the previous slide, if I want to go from here to here, the gradient descent is going to apply the entire train set here at this point, right? So, and if the data set is large, each step is going to use the entire train set, and obviously it's going to be slow. The second problem that we just talked about is that it is sensitive to the learning rate, right? So finding that learning rate itself is going to be expensive. And obviously a combination of two is that it's going to be slow for large data sets, right? So what is the solution? The solution is something called a stochastic gradient descent, or in a more general term, mini-batch gradient descent. So the idea is that mini-batch gradient descent is that it's a version of the gradient descent algorithm that it speeds up the computation by approximating the gradients. So it's not going to calculate the exact gradient, which is based on the entire data set. It's going to use a subset of data sets and basically try to calculate the gradients based on the subset of the data set. So it's going to approximate the exact value of gradient, right? So using smaller batches. So this is the idea of mini batch stochastic gradient descent. So it means that in this iteration, let's say we're here, I'm not going to imagine your train set has 1 million observations. This is train. And in gradient descent, I'm going to use all the 1 million observations to get an update, go from here, to go from this theta to this theta. Now, in a stochastic gradient descent or in mini batch gradient descent, I'm not going to use 1 million. I'm going to use a batch of that, let's say 1,000. So I'm going to use 1,000 random observations from 1 million observations and then make an update. So this update is not going to be as accurate as the previous one because we're using fewer samples, obviously, but it's a good approximation of that gradient, right? So that's the whole point of batch gradient descent. So what is the difference between batch or maybe mini batch gradient descent and stochastic gradient descent? In mini batch gradient descent, the batch size is larger than 1. So obviously you have more than one observation, let's say 2, 10, 1,000 as in this example. In stochastic gradient descent, the batch size, let me actually use a other color, the batch size is equal to 1. So this means that at each iteration, we are only using one random observations from the train set to update the parameters. As you can guess, it's going to be a lot faster, at the same time, a lot noisier. So let's see in the next slide, let's see how we can visualize this. And by the way, stochastic gradient descent has its own different upgrades. You know, we're gonna talk about it in the following slides. Okay, so here's the picture that I was referring to. It's a very intuitive one. Imagine this is our cost function, and we only have two parameters, and I don't know, you can call it theta 1, theta 2, theta 1, and this is our theta 2, right? And then this is the cost function. We can look at different contours, right? And visualize it like this. So obviously here is the minimum point. Let me use yellow, you see it. So this is the minimum point, and the goal is to get into that minimum point, right? The blue one is our batch gradient descent, and let's say the batch size is the entire train set. So I'm using the entire train set here. So I start from a random point. Let's say we start from this random point. And we use the entire train set. We find the right direction going down these counters, or going down the surface of the cost function. And because we're using the entire train set, this is going to be accurate approximation of the gradient, right? So we know the exact size and magnitude of the direction of the gradient, and we go along that direction, the opposite of that direction, right? Then we repeat this process, and as you can see, this batch gradient descent, or using the entire train set gradient descent, is going to be very stable because it is clear that at each point where direction should we go, because we're using the entire data set. The mini batch, let's say we start from here, I don't know, maybe we start from this point, it's going to be the less stable, but at the same time, it's not that awful because we're using, I don't know, maybe hundreds or thousands of this training set. So sometimes it goes in a not necessarily the right direction. Here, look at that. It's going in the wrong direction actually, but it's going to fix it up quickly because again, these are better approximations of the gradient compared to purely a stochastic gradient in a sense. Eventually, we're going to get there, right? And then finally, for the stochastic gradient descent, let's say we start from here. The problem with that is even at the very first point, we can go in the wrong direction. And that's a problem because we're working with only one sample from the train set. So the bad news is that it's not going to be stable, but the good news is that it will get there. It will get there because, again, this is random sampling, and hopefully we get enough good random numbers down the road that can lead us to the optimal value for gradient, right? So what is the plus side? It's going to be super fast, super fast, because for each update, we only need one observation, and this is very key. Okay, all right, and as long as your cost function is continuous and differentiable, let's say it's well behaved, this stochastic gradient descent is going to work, right? And of course, but sometimes, again, in machine learning, the cost functions are usually well behaved, right? But in neural networks and deep learning, the cost functions are not as simple as this, right? So there are going to be, in the later parts in the course, we are going to visualize some of the cost functions in neural networks, and it's going to be super noisy. You know, this is something like that. It's a surface like this, and then you're trying to minimize over this. So for that, we need to go even beyond a stochastic gradient descent. So the idea is that why we should go even beyond this stochastic gradient descent is usually for deep learning. When the loss function is not necessarily well behaved, it's difficult to optimize. So here is a paper that visualized the loss landscape of neural networks, and as you can see, it is very noisy, right? And we have so many local minimums all around the place, and hopefully we are trying to get to this global minimum, right? So it's going to be difficult to get there because imagine, let me actually visualize it in two-dimensional space. Imagine we have something like this, right? And if I start from here, and if I use gradient descent, batch gradient descent, mini batch, or stochastic gradient descent, the algorithm will get stuck here because at this point the gradient is equal to 0, no update. If I start from here, the algorithm is going to get stuck here. If I'm lucky and it starts from here or here, I get to the global minimum. But how can we fix this? So the way to fix this is by designing an adaptive learning rate, right? So this learning rate should work in a way that it adapts to the loss landscape, right? So for example, it needs to incorporate the previous values of gradients as well, right? So we call this momentum. So rather than just looking at the current gradient, it needs to take into account the previous weights updates as well, right? So for example, if you're doing something like this, if the gradient is, I don't know, here's high, it's going to take larger steps, here's going to take smaller steps, but at the same time, it's going to take into account the previous weight updates. It's going to give this thing, imagine of it as a rolling ball down the hill, enough momentum to pass this local minimum and then go to the global minimum. So that's the idea at a very high level and in a very nutshell. So this is a point of what we call momentum, and it's a very effective way to for finding the global minimum in neural networks. So these extensions that using momentum, there are different versions of them, namely ADAM, ADA-delta, ADA-grad, and RMS prop. So these are the more commonly used, especially the RMS prop and ADAM when it comes to optimizing the loss function for neural networks. But for machine learning algorithm, usually the cost functions are very well behaved or compared to this ones, and the stochastic gradient descent should just work fine. All right, now I think we have all the moving part of this puzzle. Now we can put it together and see how do machines actually learn. So this is a very important part of this video. It's actually the last slide. I want you to pay very good attention. So what do we do? As a researcher, we have a research question in hand, we have some interesting hypotheses, we collect data, and we start to build a model and see how that model make predictions, right? So step one, we are gonna actually, let me plot our black box. This is our machine learning thing. And there are some inputs. The inputs are X's and Y's. And if it is a supervised learning model, right? And I'm going to divide it into three parts. Train, test, split. If the data set, train, test, and validation. If the data set is small, we're going to do train, test, and divide the train into using cross-validation, right? And then we are going to come up with a structure for the model. Depending on the type of the data, we use different architecture. So for example, if you're dealing with a structured data, we can do linear regression, we can do random forest, we can do XGBoost, we can do KNN, different machine learning models. If it is unstructured data, we know that we would be better off using neural networks or some deep learning models, right? So whatever it is, we are saying that, okay, this is the architecture of the model. It's a function of inputs and the parameters of the model. The parameters can be the weights, can be the hyperparameters, and etc. Okay. The next step is to initialize these values for parameters and hyperparameters, and we do it randomly. So random initialization. So we say, okay, W can be some random stuff, random numbers. The hyperparameters can be some random numbers. And then with that, let's go ahead and use a train set and start training the data, training the model, right? So how do we do that? By using these values, we're going to come up with some predictions, right? Because remember, we do have the weights now. It's a random number. Based on those weights, I can apply it, use the original data X, and come up with some predictions, Y hat, right? So we make predictions in the train set and validation set. And at this stage, we don't make prediction on the test set yet. It's too soon, right? Because we haven't optimized the model yet. So then we have these predictions, we have the actuals. With predictions and actual, we are going to look at some performance matrices, right? So for example, we look at MSE in regression, we look at accuracy in classification, and etc. Right? So we now have a sense of what is the performance of the model in the train set, in the validation set, right? So at this point, the model should perform very poorly because why? Because we started these weights randomly, right? So this is obviously not the answer to the model, right? So it's time to optimize those weights. How do we optimize those weights? We're going to use, again, if it is machine learning, well-behaved cost function, we can do gradient descent. If you want to speed it up, we can do a stochastic gradient descent. If it is giving you a hard time kind of functions, cost function, we have to use some more advanced solvers like Atom or RMS prop, right? So, but in either case, at this point, I want you to pay attention. These happen simultaneously. This is step number 7. The optimizers, the solvers, update the parameters, these weights and these, let's say, just only the weights of the model using the train sets, right? So this is the learning part. This is what we call the model is learning something, is learning those weights, right? At the same time, pay attention here. We're updating the hyperparameters of the model using a validation set. And again, if the data set is small, using cross-validation or iterative cross-validation, k-fold cross-validation, right? But anyhow, at the end of this step, at the end of step 7, we have an optimized version of the weights here, right? So this is iteration number 1. So the weights have been updated, the hyperparameters, let me show them with D, have been updated as well. We're going to go through this process one more time. And then look at the performance. If you're happy, we move on to the next step. If you're not happy, we iterate through this thing, okay? Until we get to a point that we are satisfied with the performance of the model in the cross-validation set, right? After that, we go to the last step, which is, okay, let's go ahead and look at the performance of the model and see how we can deploy it in the wild world. And hopefully your model is generalizable. It means that it performs decently in a data that has never seen before, right? So this generalization is key. So the end goal of machine learning is to come up with a model that can generalize well, that can make predictions on the never seen data. All right, so that was it. That was our relatively 1 hour long journey of reviewing every concepts you need for the deep learning course. So I assume that you have a little background in machine learning, and after this video, we should be all in the same page and ready to go to the next step. Okay, so that was the part one. In part two of machine learning, I'm gonna review three of the most successful machine learning models, and basically they're all boosting models: XGBoost, CAT boost, and LightGBM. Okay, until the next one, take care.